Okay, so today I am trying to add a little bit spice to our class lectures by taking them outdoors. So we talked about the Gauss-Markov setup and mentioned that they have some advantage, at least in the case where we are working with y bar as the least square estimator. Now we shall see that if the assumptions are met, that is, those Gauss-Markov assumptions are met, in that case, any least square estimator has certain good properties for any linear models. So let's quickly recall the Gauss-Markov setup. So we had this thing y equal to x beta plus epsilon, that is any linear model, and I have reminded you about the sizes. So there are n rows and p columns. And the Gauss-Markov assumption, the Gauss-Markov setup has been written as y tilde 0 sigma square I, which is very much like the multivariate normal notation, where the mean is 0 and the covariance matrix is sigma square I, which captures two things in one notation. All the variances are the same, the diagonal entries are all sigma square, whereas all the off-diagonal entries, the covariances, are all 0. So all these things are uncorrelated. So assumption is only on the first two moments of epsilon. Now that's the Gauss-Markov setup, but for the time being we shall make one further assumption, and that will be a simplifying assumption that we shall relax later, namely the X matrix, the design matrix, is such that X transpose X is an invertible matrix. In this case, least square estimator will be unique and is given by the simple expression beta hat equal to X transpose X inverse X transpose Y. We want to see various interesting properties or optimality properties of this particular estimator. Now observe that this is what is called a linear function of y. It is a matrix, a fixed known matrix, pre-multiplying the vector y. So our data were y, and we are pre-multiplying it by a known matrix. We want to find its expectation, we want to find its variance. For this, let's quickly recall how we compute expectation and variance. I mean, by variance, I mean the variance covariance matrix of a random vector. So suppose I am given some random vector, which I am denoting by this red vector, vertical little vector. It is pre-multiplied by a fixed matrix of appropriate order, which I am denoting by the cyan rectangle. So if I take expectation, then expectation just passes through this cyan rectangle and it will give you expectation of that matrix times that vector equal to that cyan matrix into the expectation of that particular vector. So the expectation will enter through, what should I say, that cyan matrix, so to speak. Okay, and if I am working with the variance, the situation is pretty similar, where the variance will enter through the cyan matrix. The result is you will take the variance term of this red vector, that will be a matrix. You will pre-multiply it by the cyan matrix, the constant matrix, and post-multiply it by its transpose. So remember, you are pre-multiplying it by the matrix as it is and post-multiplying it by the transpose. Now if you apply this result and the last one onto this beta hat formula, where this part is that fixed matrix and this y is that random vector, then it is pretty easy to check that expected value of beta hat will be just beta. So it is unbiased. Whatever is the value of beta, beta hat must be unbiased. So expected value of this should be beta hat. By mistake I have written just beta. In fact, not a mistake, the hat is there, which you can hardly see under the black line. And similarly, variance of beta hat, which is not very appetizing, it just happens to be sigma square times x prime x whole inverse. You just apply the formula blindly. in one line you will get these expressions. Now the first one is interesting because it says that beta hat is actually equal to the expected value of beta hat is equal to beta. Now when you do this, remember you are doing the simple thing. If you are taking expectation of y, what is that? Expectation of y means this being fixed, it will come out of the expectation plus expectation of y, which is 0. So expectation of y is simply x beta. Similarly, if you take covariance of y, what will that be? This is an added constant, plays no role. It is same as the covariance of epsilon, which is sigma square I. Using that, you will get variance of beta hat is this. Now, one interesting fact about this is we assume that x here is x prime x is non-singular. Now, if it so happens that it is very nearly singular, that its determinant is pretty close to 0, in that case, this thing is going to blow up because this has the determinant term in the denominator, and which is expected. So, if it is exactly singular, in that case, you are not going to get any unique beta hat. So, if it is nearly singular, you expect that it is sort of approaching towards non-existence, non-uniqueness, that is, it becomes highly variable. So its variance goes up a lot.